Welcome to Northern BC Narrative on Location. Today, we have an amazing person by the name of Malhar, a professional astronomer. Am I right?
Yeah.
Mr. Malhar, it's a pleasure to have you. We're going to talk so much today that the cameras are going to explode. Talk about who you are and what you do.
Yeah, so I'm a professional astronomer at Dominion Astrophysical Observatory, which is run by National Research Council of Canada in Victoria, and I'm also a president of Prince George Astronomical Observatory, which is here in Prince George by Westlake. And in my day-to-day life, really, nowadays, most astronomers, we don't look through the telescope anymore. So our computers does pretty much everything, and we just sit behind the computer monitor and write our codes. The codes are basically telling the telescope what to do throughout the night, and we prepare our nightly. We call that as a script. With targets and the location of the target and everything, and then so we can go to bed early enough and not stay up all night long like back in the day before trying to focus the telescope and filling up the liquid nitrogen.
Liquid nitrogen.
Liquid nitrogen we used to use, we still actually use in the DAO, Dominion Astrophysical Observatory, when I'm using the one of the specialized instrument called spectrograph. Okay. We use that instrument to take the spectrums of the stars, to stars, galaxies, supernovas, to study their properties. How far away the object is and how old the object is, and we need all our sensors, all our CCD cameras. So it's a specialized camera, just like we have DSLR cameras in astronomy. We have charge coupled device camera, which are thermoelectrically cooled cameras, so the electrons are flowing at a very high rate through different dark currents, and to do that, we use liquid nitrogen, which keeps the camera cold throughout the night. Although you have to fill that up every 3 hours, so you have to stay
every
up.
3 hours.
Yeah, so you have to stay up all night long to do that.
What happens if he doesn't? Does it stop when there's no liquid?
Oh yeah. The camera warms down, and to plus 40 or even plus 50 degrees, and that's no good to do science. So you won't actually get a proper science data. But that's for one specialized instrument. We have another one called a regular CCD imaging camera. So that is always at cryogenics temperature, at minus 120 degrees Celsius. Yeah.
That is so interesting. So what happens if the camera runs out of that liquid? Nitrogen,
liquid nitrogen,
right?
You mean if there is no liquid nitrogen?
Yeah, what happens? Does the camera probably have sensors? Does it shut itself down, or does it explode?
No, it doesn't shut itself down, unfortunately, but we have been actually trying to work on that process and writing codes to, whenever the liquid nitrogen there is no more liquid nitrogen in our doer, so it should shut the camera down, and it does give us the alert on our computer monitors that the CCD is warm, the camera is really warm, so get the liquid nitrogen in the camera again. But it doesn't shut the camera off yet. So we have been actually working on doing that. It's a long process.
So what happens? Does it? Okay, so let's say, what happens if you get really warm? The sensor burns, or it's finished, right?
There is a chance of sensor, it can burn if the outside temperature is really warm, because the camera sometimes actually adjusts with the ambient temperature outside. And actually, as a matter of fact, a couple of years ago, when I was observing from that telescope, the sensor, one of the sensor for that camera actually was burned because the camera got too warm, because it was 32 degrees out. So that wasn't really good, and it took about a week for them to fix that. But so that is always it's expensive.
How much is it, for example?
About $15,000
per sensor.
Yeah.
Oh my God! How many sensors on the camera?
32.
32. What is that? Okay, what's the calculation? So 32 times 15. What is that?
I don't know. It's expensive though. It's very expensive, and it's that big of a sensor. The camera is that big. Yeah.
That is insane.
Yeah, it's a massive CCD camera. Yeah.
How big are the sensors? Are they probably
it's about 32 So each sensor is 32 megapixel.
Megapixel.
Yeah. So it will be about 6 inches by 6 inches each sensor. Yeah. So it's huge. Yeah. I mean, this is not even that big of a CCD. We have other CCDs which are
Even bigger.
even bigger. Yeah. Size of a school bus, for example.
Really?
Oh yes.
Size of a school bus.
Yeah. Yeah.
How much would that cost this program?
Oh, millions of
Millions of dollars.
Yeah, easily. Yeah.
You know, when full frame cameras came out with the full frame sensors, everybody in the film industry, they were so excited.
Yeah.
They're jumping up and down. And now you tell me, imagine.
Yeah, I know. Yeah. Well, full frame cameras are really good. Actually, a lot of amateur astrophotographer, even in town, actually, they use full frame DSLR cameras to do astrophotography, taking just pictures of the night sky, like Milky Way or the northern part of the Milky Way, or even deep sky photography, with like Orion Nebula or stuff like that.
How does it work? What type of a telescope do you? How much is the telescope gonna cost?
That's a good question. So it really depends, on what kind of telescope the person wants to buy. But the telescope usually for astrophotography, you need a specialized mount which can actually track the night sky.
Is it the one with the electrical one?
That's right.
I remember.
That's right.
Remember the ones you used to twist and turn. And
That's right. Those cost about $3,000-$4,000.
The knob ones.
Yeah, the knob ones are cheap. The knob ones cost about anywhere from $400 to about $1,200 or so.
It was crazy, right?
Yeah.
You gotta sit there forever.
Oh, that's right. Yeah, and
you build big flutter.
Absolutely. But yeah, nowadays, in astronomy, everything is turning robotic.
Yeah.
Right. So it's much easier for astronomers like us who don't want to, travel all across the world just to, observe for maybe 2 weeks.
Yeah.
Right. Last year, I was observing one of the telescope which is in Mauna Kea, in Hawaii. Yeah, from Prince George. So, it's much easier nowadays. So all you have to do is just write a scientific proposal, and then it's a peer-reviewed process. So there's a high committee that looks at the proposal, and then they decide how much time an astronomer would actually get, and then they're like, if you want to come out to Hawaii and observe, sitting inside the control room of the telescope, then you can do that too. But it's Mauna Kea, it's Hawaii, it's really expensive, so it's easier to just observe from Prince George,
Yeah. Oh, it's amazing they give you these options, eh?
Oh yes, yeah. It's a privilege, to be honest, getting time on one of the world's amazing telescope, really, and observing from that telescope, even though from Prince George,
Imagine that because you fly there, you get jet lag, you're tired already, dehydrated, and then you have like 2 days, right? You're like, oh god.
Yeah. Oh yeah. Yeah. It's tough, because my wife and I, we were in Victoria in 2022. I had 26 nights on the Plaskett telescope, which is in Victoria. And out of 26 nights, I had 23 clear nights. All right. And I had to stay in the dome all night long and observe. So I was just exhausted after 23 nights of observing and sleeping during the daytime, like most people think that astronomers do.
You're right. You have to sleep. It's a midnight shift.
That's right. It was a graveyard shift, basically. Stay all night long in the dome, and sleep for 4 hours.
Are you allowed to bring like coffee in there, or?
Oh yeah.
Oh yeah.
Oh yeah. Oh yes. Yeah.
Oh,
we
sometimes
can
like
bring food, coffee. Yeah. Yeah. So it was, when you have the coffee, so you can stay up and
boom.
Yeah. Oh yeah. So that was a big help. But yeah, after observing all those 23 nights, that was tiring. But you don't get bored.
What do you see?
So I was studying a very specific type of stars. They are called eclipsing binary stars.
What is that?
So there are two stars very close together, and they're orbiting at a center of mass. So they're orbiting really fast at a 200 to 400 kilometers per second.
And then they don't clash?
No, they don't. Eventually they do after a few million years. And we can actually calculate the orbital period of those stars. And the technique that I was actually using to calculate their velocity, the speed at which they are orbiting each other, is called a radial velocity. Right. So radial velocity basically gives us the Doppler shift, meaning. So one star, when you're standing here, for example, and you hear an ambulance coming here. So when the ambulance is coming towards you, you're hearing a sound really loud. And when it's directly perpendicular to you, it's the least amount of sound. And then it's when it's going away from you, you hear less and less sound. So that is actually a Doppler effect. So there is a red shift and a blue shift. Blue shift is coming towards you, so the ambulance is coming towards us is a blue shift, and the red shift is ambulance is going away from you. Right. So in those star systems, one star is going away from you, and one star is coming towards you. Right. So they're orbiting at a circular or sometimes elliptical path. And so that's what we were actually studying.
So what is in the middle? What is the mass?
It's just the gravity.
So the gravity is the two planets pulling each other? Or
two stars. Yes, that's right. And sometimes what happens, there's a mass transfer effect. So the star sometimes gets too close to another star, and the other star sucks the mass out of the other star.
When you say mass, you mean
all the
debris or
debris. That's right. Yeah, it sucks all the debris from the other star, right? And eventually, the other star cannot actually have any more mass inside it, and then it will explode into a supernova or a nova, depending how big the other star is. So it's really cool.
What happens? Okay, so when it explodes, what happens to the other star?
It gets ejected. Yeah, it just goes. Then it turns into an orphan star, meaning the star really has no companion. So it gets ejected because of the gravitational effect and the explosion, the shock waves, because the explosion is just massive. Let's say about, 10 trillion nuclear bombs dropped at the same time at the same location. That is
crazy. So the debris, what happens to it? They go and become one with that planet?
That's right. Well, yes, it actually could happen.
So you just what happens?
Crushed.
But then you have
a neutron star.
So this one explodes. But this one has all the mass of the other star.
No, the mass of the other star, which has the bigger star, that's the one which explodes, and the smaller star just gets ejected because of the shock waves.
Sorry, I'm so excited.
That's right.
So the smaller star, right?
Yeah.
That's the one that this mass got taken away.
That's right.
Oh, okay. So it's like, okay, I have no use for you. I'm gonna blast you.
That's right. Yep. Yeah. Because that star's job is done, and now it's getting kicked out. Right. Which sounds terrible. I know, but.
Oh my God, man.
It's the same thing happens in the type 1A supernovae, right? Like one of my main research is looking for supernovae and studying the supernovae in the universe. So in the type 1A supernova, there is a high mass star and there is a white dwarf. White dwarf stars, two different stars, and white dwarf is a more massive star, but it's a smaller one. So, for example, take the entire mass of our sun and put all the mass into a ball which is 25 kilometers in diameter. So that's really small, and the sun is really big, right? The mass of the sun is 3 million Earths. Something like that. So the sun is really heavy. I don't know the exact numbers of what is the mass of the sun. But anyway, so the white dwarf star is usually an extremely heavy star, and the red giant.
So it's heavier than the sun.
Oh yes, always very heavy.
Why?
Because it's a smaller star, but it has a mass of the sun, right? So our sun has a diameter of about
Yeah.
17,000, a radius of 17,000 kilometers, or even more actually. And the radius of white dwarf star is only 10 kilometer. So it's really small.
10 kilometers.
That's it.
Oh, wow.
Yeah.
How the heck does it doesn't it?
Exactly. Right.
It's like all made of solid metal or something.
Yeah. Yes. That's what it is. Yeah.
Let's hope they don't go and extract it.
Oh no. No, all these stars are really far away. You know, our sun is a single star, and it's not gonna. You know, the sun will eventually explode, but we still have about 6.5 billion years to go for the sun to explode. So the Earth will be dead long before that. Sounds dark, but you know, yeah.
So the dwarf is much heavier.
Yeah.
And then you have the other one. What was the other one?
Red giant star.
So what is it? What's this red giant?
So a red giant star is when our sun will. I'll take example for the sun. So when the sun will actually, it's into its last stage of life. So the sun will actually expand. Okay, will get bigger and bigger. Okay, and eventually it will get so big that it will actually swallow Earth. So yeah. But we still have a long time. Okay, so that our sun will eventually turn into a red giant star, and we have tons of red giant stars out in the universe. When we have a white dwarf and a red giant star, of course, white dwarf is heavier. So white dwarf is again also sucking all the mass, all the matter of the red giant star. Okay, and then it's creating like an accretion disk, meaning it's a disk of all the debris and all the matter around the white dwarf star.
So like Saturn almost?
That's right. Yes, exactly. Yeah, it's like a ring. Yeah, right. And eventually, the white dwarf star is actually accumulating all that matter from the other star. It's stealing all the mass, basically. Right? Yeah, those are. Eventually, white dwarf star's core actually gets very destabilized because it cannot handle any more mass from the star, and then that causes the nuclear fusion, and that's when the white dwarf star explodes into a massive explosion called a supernova type 1A. And the other star gets ejected. Its job is done.
It looks like a lot of things in our life.
That's true.
You know what I mean? Everywhere. In our society, everywhere you can see.
That's right.
Wow. You see, it's coming from somewhere. Okay, so. Okay, just it's so interesting. Okay, go ahead, tell me more.
Yeah, so those kind of explosions are actually one of the most important explosions in our universe to study the age and the expansion rate of the universe, meaning how fast the universe is expanding.
So when this thing, so it gets all the mass and it explodes, does it become a gas giant? Or?
Yes, after the explosion, what happens? It releases all the gases, which is mostly hydrogen, helium, carbon, atomic oxygen, atomic nitrogen.
What is atomic oxygen and nitrogen?
Just molecules of oxygen, right? Just in the same in a little bit of different wavelength. That's I shouldn't say atomic oxygen actually. Atomic oxygen is only on the surface of the Earth. Oxygen, right? Oxygen, nitrogen, helium, hydrogen. Hydrogen is one of the most important element in the universe. And the leftover gas from the supernova explosion, we call that as a nebula. Right? And nebula, and that's where all the stars are actually being born inside the nebula, because there is main elements that we need for a star to actually to born, which is hydrogen and helium, right? And all the gases comes together. It forms denser parts. There are denser regions in that nebula, and then due to tidal forces, the gases are getting stronger and stronger, compact and compact, and that's when you see a protostar, which is a baby star. And then the protostar eats more and more gases, mass around it, debris, and then that's when you get a newborn actual star.
This is very complex. So I'm just
It
gonna
is.
walk through it with you because I want to understand. So, what happens? The star takes most of the mass from the other star.
Yeah.
Then he explodes, right?
Yep.
And then it becomes a nebula.
That's right.
So within the nebula, all the gases in there use all the debris that it took from other places,
That's
and they
right.
make their own star.
That's right.
That is
That's right.
insane. Where is all this energy? Where does it come from? Because the gas doesn't make any the only you know what I mean, right? So this thing explodes, but how does it? Because you think when it explodes, it's done, it's finished, right?
Yes.
Right. Then it's creating more stuff.
Oh, yes.
Right. So this stuff is it bigger than other?
Oh yeah. Oh much. Yeah. Nebulas are
Yeah.
incredibly big
Yeah.
objects in the
Yeah.
universe. You know, one of the beautiful nebula that you can actually see with your naked eye from here, from Prince George, it's called an Orion Nebula.
Orion.
Yeah. M42.
M40.
Yeah. Tonight it's going to be beautiful.
Yeah.
The sky is going to be clear. And March 17th, right? Today, yeah. And so if you look in the extreme south direction, you will see an Orion constellation, Orion the Hunter.
Yeah.
Right, and just below the Orion's belt, you will see three stars aligned like that, and the middle star, this one, it's the Orion Nebula, and you can actually see that with your naked eye, and that is one of the very few deep sky objects that you can actually see, you know, without having a telescope, without using a telescope, or even without using the binoculars. Yeah.
That is amazing. Okay, let's go back to nebula. This is my favorite subject, right? So I don't talk about it. I don't, So okay, so this nebula is huge, right?
Yeah.
So what happened that when it explodes, what does it do? Does the shock wave pull everything?
That's right. Yes.
Or does it pull also? Does it do both?
It pulls out, and then over time, the gas is in some parts of the nebula, the gas is getting closer and closer to form new stars. Right. That is due to gravitational accretion effect. Right. And when that happens, so there is a lot of dust and debris and all, in the universe, and especially when a massive star explodes. Okay, so when you have this dense region in the nebula, where there is a lot of hydrogen and a lot of helium, which are the two most important elements in the universe, right? And when you see those dense region in the nebula, then those are forming new stars, and that is mostly happening because of the gravity, because the dense region are getting closer and closer, making those regions denser and denser day by day. Yeah.
This is insane. So how many stars are born in this nebula? How many planetary bodies? How many moons?
That's a very
how
good question.
big is this thing? Because I'm getting an image, right? I'm just like it's so vast. I cannot.
That's a really
more
good
RAM.
question. Yeah, so that's a good question. So in our galaxy, in our Milky Way galaxy, we have thousands and thousands of nebulae. Okay, so just in our Milky Way galaxy, you would expect that we'll see a lot of stars being born each year, right? But no, only 4 stars are being born each year in our Milky Way galaxy.
Why?
Because our Milky Way galaxy is at a quiescent stage, meaning we haven't seen a supernova for almost 650 years in our galaxy, right? And the other nebulae that there are out there in our Milky Way galaxy, they are old, and they're just now expanding, and some of the nebulae are just very quiet. They're not really doing anything anymore because the stars were already born in those kind of nebulae, and then that's it. Now it's just a cloud of gas and dust. But some nebulae, like the Orion Nebula, actually, that is an active star formation region. So in that nebula, you can actually look at the stars, which are baby stars. You need a big telescope, of course, to see that. But in Orion Nebula, there are at least 4 stars being born each year, and we can actually see them.
That is insane. Okay, so there's so many questions. Okay, so how did our how did a galaxy created? Was it like a super?
Supernova? No. That is a good question, and one of the hardest question to answer for any astronomer.
Is that?
Yes, how the galaxies are formed. We don't really have a clear answers on how these massive, structures are formed in the universe, and we have just insane amount of galaxies in the universe. And we don't really know how they're formed because galaxies are huge. They're just massive. Our Milky Way, for example, from one point of our Milky Way to the other point is about 150,000 light years across. So it's an incredibly big galaxy. But our Milky Way is not even actually that big. Our Milky Way is really small. Yeah. So our Milky Way has about, I'll say about 250 to 400 billion stars.
That's a lot of stars.
Just in our Milky Way galaxy. And we have about at least 200 billion galaxies in the observable universe. Each galaxy has at least 500 billion stars or even more. So we are quite insignificant.
Like a flea. So a galaxy, right?
Yeah.
What is in the center? Because I think the more you come out, right? Like it gets dimmer, but the center is so bright. What is in the in the center?
That's a good question. So the central part of the galaxies, at the center of most galaxies, there is a black hole, a supermassive black hole. Okay. But black holes they're not emitting any light.
Okay.
Right. But at the core of the galaxy, apart from black hole, we have just tons and tons of stars and a lot of dust, right? So that's why we see, for example, our Sagittarius arm, which is the center of our Milky Way galaxy, right? So Sagittarius arm, you will see like a giant dust all across the sky when you're looking at the galactic center, right? Which is really cool to look at. From Prince George, we cannot actually see the entire Sagittarius arm because we are too far north. But if you are somewhere in, like in Arizona, for example, in the United States, you will see Sagittarius arm, or even better in Southern Hemisphere, like in Argentina or Chile, you will see Sagittarius arm, the entire Sagittarius arm all across the sky. So the Sagittarius arm is so bright. The center of most of the galaxies are so bright because there are dense population of young and middle-aged stars. Yeah.
So these stars, right? Do they have a planetary system around them too, or no?
Oh, most of the stars in our galaxy does.
So most of them have. Okay.
Yeah.
So there's a massive black hole in the center.
That's right.
Why is it not sucking all these things in?
That's a very good question.
Because like in the movies.
Yes. So our black hole, as compared to our galaxy, it's really small. Okay. So although the mass of our black hole is called Sagittarius A star, the name of the black hole at the center of the Milky Way, the mass of it is about 1.5 million times the mass of our sun. So you have about million suns in an object which has a diameter of 25,000 kilometers.
Wow.
Yeah. So it's really dense, and you cannot see the black hole, of course, because they're not emitting any photons, and it's black. And nothing comes out of the black hole, it goes in. So why our black hole is not sucking everything? Because our black hole right now is at a quiescent stage, meaning our black hole is quiet, right? Periodically, you will see if there is a dust somewhere close to the black hole will suck that dust inside, and then it will create a small, like a outburst. Right. So the last outburst from our black hole that we saw, that was in 2012. That was the last one that we saw, and now it has been quite,
What happened exactly?
So there was a dust of about 1 light year. So it was a big cloud of dust.
Yeah. So when you say dust, are we talking about rocks, asteroids, and things like that?
Rocks, yes, a lot of asteroids, right? And a lot of helium, hydrogen, and all sorts of elements, heavy elements in our universe. So the dust was orbiting the black hole for a long time, okay, and slowly it was getting closer and closer, and we knew that it will suck all the dust eventually one day, and that happened in 2012.
Was it violent, or what was it?
It was. Oh yeah. It's always violent when any black hole is sucking anything. You will always see some flashes coming out from the event horizon of a black hole. Actually, the accretion disk, not the event horizon, because nothing comes out of the event horizon, right?
What is the event horizon?
Event horizon is
so
the
much
first.
to talk about. You're not gonna leave here today.
The event horizon is the most complicated and most interesting part of a black hole. So it's the first part where everything gets sucked in, right? And we don't really know where it goes when it goes inside the event horizon. So we can see the objects going inside the event horizon, but we don't know what happens when it goes.
On the other side.
On the other, or if there is any other side, right? We do think from our equations that all the matter that gets sucked into the black hole, it goes to a point called singularity, which is a really tiny point in a black hole. But what happens when all the mass, all the objects goes inside to that point called singularity? We don't know what happens after that because we just do not have information. We just don't get any information about that. Even we don't get any information about what objects going inside the event horizon. So this is just theory, Einstein's special theory of relativity and general theory of relativity.
That is, you're so good with math. It was my worst subject. That's why I never became an astronaut. Okay, so when you sucked all this dust in, like what happened? You just like a firecracker exploded?
Yes, exactly. That's what happens. Yeah, it goes to periodic outburst. And we don't really know why that happens. In 2019, I discovered one of the an event called tidal disruption event, okay, TDE. So a stellar mass black hole is actually, I wouldn't say a stellar mass black hole, sorry, it was a supermassive black hole, about 2.5 million times the mass of our sun. So massive black hole, much bigger than our Milky Way one. So that black hole sucked a high mass star inside it, right? And the star was actually getting pulled like a elastic band when it was dying. So it created an incredible amount of flashes. It was really bright because the black hole was very active at that point, and it was active for about 21 days. Until
suck everything in 21
that's
days.
21 days. Entire star. Like 100 times bigger than our sun.
And he sucked it all in.
All gone.
This is crazy.
That was actually one of the closest tidal disruption event that we have ever observed.
And it was violent and crazy. And So you just sucked the star, or did you suck all the planets around it too?
We can't tell if there were any planets around that star because it was just in other galaxy. It was about 350 million light years away from us. So that actually happened 350 million years ago.
It takes that long to get there.
That's right.
I'll talk about that a little because there's a huge lag, right?
Everything in the universe that we actually see, even with our naked eyes, right? There is delay in time because the light travels at 3.00 times 10 to the power 8 meters per second squared. So it is the fastest thing in the universe that can travel, and Except in our solar system, actually. So in our solar system, we can observe planets, which are in real time, but our sun is some 7 or 8 minutes delay.
8 minutes delay with the sun.
Yeah. The light coming from the sun.
Oh, it's crazy. How far is it from us?
It's about 150 million kilometers. Yeah.
What would that be in light year? You don't need light year for
No, it's not even a light year. In our solar system, we don't even talk about light year because the objects are relatively close. But once we are outside our solar system, that's when the light year comes in.
Yeah.
Because, so our solar system from one point to another point is 1 light year.
Our solar system.
Yeah, our solar system is massive. It's big, so we cannot go outside.
Make
our
it look so
system.
small, right? Like everybody, I never
right.
thought, oh, you 1 light year?
Yeah. So for humans, we travel faster. I think 5 times the speed of sound. I think could be wrong. It could be more. So for us, it will take about 150 to 160 years to go outside our solar system. So really, that's not possible.
So dog years.
That's right.
Oh my God. It's just like,
So we are stuck in our solar system. Yeah. Star Trek, not real, but
I wish it was real.
Well, yeah. I mean, traveling with the speed of light is, it's just not possible. Theoretically,
Would
it's
the
not
bodies
possible.
dissipate? With the bodies, like
You will go through time dilation, and then
what is time dilation?
Time dilation is, for example, if you are traveling with the speed of light and go somewhere in, let's say, to the closest star system, okay, Alpha Centauri, which is 4.5 light years away, right? You travel with the speed of light, so you're actually leaving the time behind because the time doesn't travel faster than the speed of light.
Okay.
Right? It's weird. It sounds really
crazy.
complicated. I know, and it even sounds crazy. I know.
No, it's interesting. Now I'm learning so much. Okay. Yeah.
So, you're basically slowing down the time, right? So, for example, if you travel with the speed of light to the nearest star system, which is Alpha Centauri, it will take only 4 years for us to go there. 4 light years.
4 light years.
Yeah, if we travel at the speed of light.
Okay.
Right? But if we travel with the speed, what we do now, 5 times or 6 times the speed of sound, it will take us about 700 years to go there.
So when you say 4 years, 4 light years, that would be our 4 years. You would be in that process for 4 years.
4 light years.
When you say, what happens to the body? Like, do you die before you get there?
No.
If it's going that fast?
No. You will grow. You will be 4 years older.
That's it.
That's it. Yeah. So once you go back to our Earth after 8 years, after 8 light years, who knows? The Earth might not be even be there, or the Earth will be an entirely different place, or the humans will be on the Mars. Yeah. So the concept of traveling at the speed of light it's strange.
So my brain is blown. So okay. So let's say I move from Earth to that place for 4 years, right?
Yeah.
That's 4 human years for us, right?
That's right. Yeah.
Okay. So if I travel from here, 4 human years to over here, right?
You cannot travel in 4 human years to that star.
No, but if it's light years, it's fast, right?
Oh yeah.
So it should
like
take
4 light years.
what would it be, like 4 human years for light years?
Oh yeah.
Okay.
Oh yes.
So if I can come back again in 4 human years in light years, right?
Yeah. You will be 8 years older. 8 years human
Older.
years older.
Then, but when I
But the Earth, people we know, they will be all dead. And so we will actually go through a different. We'll see Earth as a completely different phase. We will see the Earth after 1,500 years.
So the 4 years that you're traveling, and then the 4 years you're coming back, it's not going to be equal of the 4 years here because of the speed you're traveling?
The speed you're traveling.
That's crazy.
It is. Yeah.
So basically, the 4 years that you're traveling is equal to lots over here.
That's right. Yeah. Yeah. It will be at least 600 years on Earth.
600 years.
Yeah, so it will be
Might
1,200 years.
Might come back to one.
That's right. Yeah, it will be equal to 1,200 Earth years. And for us, we will be only 8 years older because we are traveling at the speed of light.
Can you travel backward in the speed of light?
No.
Can you get younger?
No.
Okay. Crazy. Okay, so this black hole you talked about,
Yeah.
in the center of our own galaxy, is it stationary? It seems like it's moving around.
It is. Well, it is orbiting around itself. Yes.
What do you mean around itself?
That meaning it's revolving, right? Like our sun does.
Okay.
Yeah. So black holes they revolve around themselves really fast.
What do you mean? Like it's just like this?
Oh yeah, and they have a huge magnetic field.
Yeah.
Just like Earth, we have a magnetic field, right? So black holes have their own magnetosphere.
Yeah.
But we cannot really confirm how big their magnetic field is because it's really hard to tell, because we get so little information about the black hole, because what we can actually see is we can only see the accretion disk around them, like the disk, like Saturn.
What is a disk, the accretion?
Accretion disk is the material which is orbiting the black hole at 50% the speed of light. So it's orbiting really fast, and so all the material is extremely hot, right? So that's why it looks red when we actually look at it using radio telescopes.
Is this the stuff is sucking in, or it's nature?
It's nature. Yeah.
I thought because it's sucking in so much stuff, that's what you see.
No, this accretion disk eventually will go inside the black hole, but it takes a long time. So black holes are the longest lived object in the universe. Okay, these black holes will be the last objects to die off in the universe.
They kill everything and then they.
Yeah, exactly right. And for example, the smallest black hole in the universe, which we call it as a stellar mass black hole, they have a mass of 3 to 20 times the mass of our sun, so not very big, right? Those kind of black hole will take about 10 to the power 100 years to die. So 10 followed by 100 years.
Are we talking light years?
Just years.
It's too complex.
Yeah. So you have to get after number 10, you have to add 100 more zeros. 100 more zeros after 10. So that is
We'll
the
be here
age.
forever.
Yeah, exactly. That is the age of a smallest black hole in the universe.
Do they have different ages?
Oh yeah. Bigger black holes live longer. Yeah, because they suck more matter, and their diameter gets bigger and bigger, right? So they'll live for 10 to the power, 800 years.
So that disk you're talking about, why does it go inside?
Why it doesn't go inside? It does eventually, but it takes so long.
How and why?
So the disk is getting closer and closer to the black hole, so meaning the material is slowly falling inside the event horizon, right? So the black hole has an extremely strong gravity. Black holes are the only object in the universe which has the strongest gravity. Okay, nothing has the strongest gravity than black holes.
So nothing can escape it, basically.
That's right. Nothing can escape the black hole. Not even light. And we know how fast light travels, but even light cannot escape the black hole. Once it's in, that's it. Whatever goes inside the black hole stays inside a black hole. Yeah. That's why it's hard. It's so difficult for us to study them because, all the information is going inside, but nothing is coming outside. The information is being blocked, from us to actually study those objects. And,
there's no way we can probe it because it's so far away.
It's so far away, that's right. I mean, even the fastest probe will take thousands and thousands of years to go there.
Have you sent anything there already, you think?
No. The black hole at the center of the Milky Way is just too far away, 12,000 light years.
So there's one of these in every galaxy.
A supermassive black hole, that's correct. Yeah.
Every galaxy has one.
Oh, yes. Most of the galaxies that we have observed, supermassive black holes, yes. And there are millions and millions of smaller black holes, stellar mass black holes, or mid-mass black holes.
In the center or all over?
Not just at the center, distributed all over the place in the galaxy. Yeah.
It's getting scary, man.
Yeah.
So is there an example of this massive hole,
Yeah.
sucking the whole galaxy into itself. Do we have an example like that at all?
No.
Is there anything close to it? Is there anything happening already?
No, black holes usually don't suck the entire galaxies because black holes are very small as compared to these massive structures like galaxies. Black holes will never. They don't act like a cosmic vacuum cleaner.
That's what I was thinking, right? I'm like, they're cleaning everything, right?
No, black holes will never actually. They don't act like cosmic vacuum cleaners, right? They're minding its own business.
Yeah.
The objects are only at a harm if you're close to them, like very close to them, right? But if you have a safe distance between it and you, then you're fine.
So you will not even bother, even not pull the gravity, even there be no anomalies.
Anomalies. No. If there's a safe distance between the black hole and an object, then we don't have to even worry about them. And the center, like the supermassive black hole at the Milky Way, at the center of the Milky Way, it's really far away. So it will never suck everything up.
We shouldn't have said that.
No, it won't. No.
I have a question. Can these black holes suck something that is like 10 times bigger than themselves?
Oh, absolutely. Yeah, like the object that I discovered in 2019, the star was actually 175 times bigger than the radius of the black hole.
Oh, did it suck it? Does this make any sense?
The gravity. Yeah.
So then you take the star apart then?
Oh yeah. It looked like the star at the end. We couldn't see the star how it looked like, but we made simulations. We made animations on how the star looked like when the black hole was actually sucking. It was basically tearing the star apart. Yeah, so it was a pretty violent event.
It's like Thanos.
That's right. Yeah, the star was literally looked like an egg shape because.
So it was dragging it and sucking it all.
Yeah, slowly. So it was pretty.
That is violent.
Oh yeah,
that's got to be really violent.
Yeah.
Damn, such a little thing has so much power. It's insane.
We don't know why though. It's very interesting. Black holes are the most dangerous objects in the universe. Other than magnetars.
What is that? Just talk about all this stuff. What is a magnetar?
Yeah.
So before we finish this, so he sucked that star.
Yeah.
Probably did some explosion, right?
That's right.
But nothing came anywhere. Nothing came out of anywhere.
No. Everything went inside, and after 21 days, it was all gone. We actually made I actually made a time lapse video. So we were monitoring that discovery for all 21 days. 21 nights, and I created a nice animation of how the star, the bright, basically looked like a star, appeared out of nowhere in a galaxy that we didn't even know that existed in there. So the explosion was actually brighter than the entire galaxy. Yeah. So it was outshining the entire galaxy for 21 days. Yeah. So you can imagine how massive that star could have been. And how the
little
violent explosion was.
It cannot even explode. I guess if it gets sucked in, right? Even like rays and things like that.
Oh yeah. It was pretty interesting that, and it wasn't. I discovered that really accidentally.
You were very shocked when you were looking at this. Like, was your heart beating? Like, hey, like this is crazy on that scale, right? I mean, like.
Yeah, I mean, when I'm looking for these kind of events in the universe, so I come across like I'm looking for supernovae. We are trying to discover like supernovae in the universe really far away. Like high redshift supernovae, right? So we have so far discovered some 300 of them or something like that.
Supernovas.
Yeah.
Okay.
Explosions.
Is it due to the black hole or no?
Some of them were, and some of them were just star exploding at the end of their life. We don't sometimes come across these kind of objects, but this one was, was very interesting because it was relatively close and it was very bright.
Yeah.
Right. So, that's why this was a interesting one. Yeah.
You know, when you look at the stars, you're like, oh, it's so beautiful. No, I know it's like it's not beautiful. It's all violent, and
It is.
It's like this is not like a like seriously. It's
That's
like a
right.
war zone out there.
It truly is, for, when we do visual observing, just looking at the night sky from a dark location, we see the sky is beautiful, it's static and eternal. But our night sky, it's very dynamic, and there are violent explosions, astrophysical phenomenon happening every 3 seconds in our universe somewhere that we cannot actually see. So every 3 seconds, or every second, there are 3 stars dying in the universe.
And then some burning, right?
Yeah. Yeah. So you can imagine how many stars are there in the universe.
It almost sounds like the black hole or recycling and then re-emitting some or something. It's just crazy. But we have no access to that information.
Yeah. It's really cool.
Yeah, I love this field. Okay, so what was the other thing you were talking about?
Oh, the magnetars.
What the heck is magnetar? I never heard that before.
Yeah, magnetars are another scary object. They make my hair stand up.
How were they created? Or talk about the whole thing.
Yeah.
I never heard that before.
Yeah, magnetars, neutron stars, and pulsars. They're kind of a similar object.
Talk about each of them. What they do.
Yeah, so when a single massive star, about anywhere between 8 to 40 times the mass of our sun, so it's a very high mass star, okay, very big star. When it explodes into a supernova, we call it the core collapse supernova. So the core of the star actually collapses. Okay, yeah, it keeps crushing down, and the outer shell of the star keeps expanding.
How is it crashing? What is the gravity that is pulling it?
That's right. Exactly. The gravity is actually getting into crushing the star to get into a smaller space, very, very small.
Where does gravity come from? That gravity that is pulling it to, I guess.
So it has to do with nuclear fusion. Okay, so the hydrogen atoms are turning into helium atoms. Okay, and that is a bad thing for the star.
Is it heavier? Which one is heavier?
Hydrogen.
It's heavier.
Yeah.
So it's changing from
helium atom
to hydrogen.
Yeah.
So hydrogen is heavier.
Hydrogen.
That's why it's pulling it in.
That's right.
Okay.
Yeah. So all the stars that we see in the universe have about 98% of hydrogen.
Yeah.
1% of 98.5% of hydrogen, 1% of helium, and then other 0.1% of other heavy elements in the universe, like iron, nickel, and a lot of iron actually. But when the star is at its end stage, what happens is the hydrogen fuses into helium. Okay, and that actually destabilizes the core of the star. Okay, so all the mass, all the gravity is actually going down at the core of the star, and the core is actually getting heavier and heavier and is being destabilized at the center of the core. Okay, and when that happens, so it happens in seconds. When a core collapse supernova is going to happen, everything happens in seconds. In a fraction of seconds. It's insane how fast this process happens. So when the core gets destabilized, you get a supernova. Okay. So it explodes.
So it shrinks, I guess, right?
That's right.
Then it explodes?
Yep. It shrinks, and it then explodes. And after the explosion, you will always, there will be a remnant of the supernova left, which sometimes it can be a pulsar, or it can be a neutron star.
What is a pulsar?
So pulsars are the corpses of the high mass stars. So pulsars are we actually call them as the lighthouses of the universe, because there is beam coming off from the north from both sides. Yeah, and they're rotating really fast. That's why pulsars, pulsating stars. So acronym pulsars. It sounds really cool.
And how far are they going?
About half a light year.
Half a light year, these things travel non-stop.
Oh yeah. The beams. Yeah.
So is it rotating?
It's rotating.
Is it rotating
fast.
at the same time?
Yep.
Same, or do they reverse rotate?
Well, they're rotating. One side of the pole is
like this?
Clockwise. They're both rotating clockwise, but at a different time. Yeah.
That's crazy.
Yeah.
Where does all that energy come from for this thing to exist? Doesn't make
We don't know.
Just, what I'm like? Okay, everything makes sense, but these things basically dies and explodes.
That's right.
Where's this energy coming from? You know what I mean, right? There has to be something that is moving this thing, right? I'm just trying, because they don't die, they just say the energy stays, right?
That's right.
How long do they stay alive, these things?
Pulsars usually live for, I'll say, about 200 to 300 million years. Yeah, so not a whole lot. And then we got neutron stars.
Okay, so we move to
pulsars. Yeah.
So no, I'm very curious. So this thing explodes, basically dies, and
Yeah.
still is alive for all these years.
Oh yes. After the explosion, that is basically the remnant of the supernova. That is the leftover core of the star. So when the supernova is happening, that's when all the process happens to form a pulsar.
And we don't know where the energy comes from.
Well, it's the star. The energy comes from the star.
But for that long?
Oh yes. Stars burns for a long time. Yeah.
You know something? I don't know. Just came to mind. So these things explode, right?
Yeah.
And then how many million years this thing is around?
Pulsars will live for about 200 to 300 million years. Neutron stars will also live for about close to 200 million years. On the other hand, though, magnetars, they live only for a few million years.
Okay. So one thing I'm thinking here, you know how when you light a match?
Yeah.
You see it?
Yeah.
Right? This sounds like it's a match.
That's right.
Our life is so short and insignificant.
Exactly.
If we lived for like millions of years, that would be like
I know.
It'd be like, you know what I mean, right?
That's right.
It tells me like it makes us like, because like I wish we could live for billions and billions of years, right?
Yeah.
So this would be all matches burning out, and because we live so tiny.
Small. I know.
Everything is so big for us, right?
Yeah.
Okay, so this one was a pulsar, right?
Pulsar, yeah.
Let's go to the next one.
Yeah, the neutron stars. So the neutron stars are.
How is that created?
It's the same
Exactly
process.
the same.
Exactly the same. Yeah. Neutron stars are usually formed when there are more neutrinos.
What is that?
Neutrons.
What is that?
Neutrons is a subatomic particle at the end of the explosion of a star. You can actually detect those neutrinos from the Earth, from Antarctica and Arctic. There are two observatories on both north and south poles of our planet which are detecting those neutrinos from the exploding stars, right? However, when there's more neutrons, it's actually called, well, the electrons are going through. It's a process called electron degeneracy pressure. Okay, so the electrons are.
What is that?
So electron. Oh no! I'm trying to explain.
Yeah, I know it's hard to. No, because you know all these terminologies and things like that. Right?
Yeah.
So it's more difficult for you to tell me.
That's right.
But most people just like me, they don't know. Yeah. That's why I'm trying to get like the best out of the best. Right?
Yeah. So electron degeneracy pressure is when the electrons are flowing everywhere in and around the star, okay, at the end of its life, okay, and that's when the star is actually getting kind of destabilized and it's ready to explode anytime, okay, and when that electron degeneracy pressure happens, at the same time there is another process happening which is called neutron degeneracy pressure. So electrons and neutrons, they are colliding at a very fast rate inside the core of the star, okay, and when you have more neutrinos, more neutrons in the star, which are neutral in charge, electrons are negative and protons are positive, right? So the neutron atoms are getting more and more in the core of our star. And when that happens, that's when we get a supernova explosion. And after that supernova explosion, we will see a neutron star being born at the end, right? And that's what the neutron star is. So we don't really know what is inside the neutron star, but we do know that the mass of the neutron star is anywhere from 1 to 3 solar masses.
Solar massive.
Yeah.
How long did that stay alive?
We don't know. You know, and that, yeah, and neutron star's diameter is only about 20 kilometers, and so you get at least 3 suns, okay. Crush all the suns, all the mass of the sun, and put all that mass into a 20-kilometer ball. So that is the neutron star.
And
so it's incredibly heavy.
And then it stays for a long time.
Yeah, yeah. It orbits around it itself. It just rotates, but it's not as fast as pulsars.
No.
Pulsars are rotating really fast.
Yeah.
They'll finish one rotation in 89 milliseconds. Yeah. Our Earth takes 24 hours to orbit around itself.
Yeah.
Pulsars takes 89 milliseconds to orbit around itself.
Yeah.
So it's incredibly fast. Yeah.
How much light does it give?
Not a whole lot, actually. Not a whole lot. Although they are bright objects, you will see them, like one of the pulsar that is actually visible with the regular optical telescopes that we see every day. Not every day, but whenever you see the optical
Even
telescopes.
it doesn't snow here.
So it's a supernova remnant that the supernova actually exploded inside our galaxy in 1054, July 21st. Long time ago. It was first discovered by Chinese astronomers, right? And that supernova explosion was visible for almost 2.5 years. You can see that explosion even during the daytime. So it was that bright.
Even the night probably.
That's right. It was very bright, like 5 times the brightness of the moon. So it was extremely bright.
Imagine if we lived in those times. That'd be so fun,
right?
To see it. I'm so excited about stuff like that.
Yeah. So, so that happened in 1054 AD. So that was, like 1,000 years or so ago. And now we can actually see the remnants of that supernova. We call that as a Crab Nebula.
Why Crab Nebula?
Yeah, it kind of looks like crab.
Yeah.
It's in a constellation of Taurus. And inside that Crab Nebula, you will actually see the pulsar.
Pulsar.
Yeah, which is the rapidly rotating stars, and you can see the kind of ripples created by pulsar.
What does a pulsar do? Does it create like more planets? Does it suck more? What's the functionality of it?
Really, there is no functionality. They sometimes pulsars can act like a cosmic clock, really. Very high precision clocks.
Also,
to measure their time scale and how fast they're orbiting, and then we can compare other neutron stars orbit with the other pulsars and how they're orbiting. We can calculate their orbital phase. There are so many things. So this is pulsars are really cool objects to study for radio astronomers. It's whole another field in astronomy. You use radio telescopes to listen to the pulsars, so you can actually listen to them.
What does it sound like?
It's scary. Sometimes you hear a static in your radio.
Yeah.
That's how the pulsar sounds like. Yeah, it's weird. It's a weird sound, honestly. Because they're rotating so fast, right? So, we don't know why they sound like that.
They're destroying things around.
Yeah,
Everything is killing each other.
I know. Universe is, it's weird.
I thought it was this beautiful thing. I'm like, I don't want to even look at the stars.
Yeah.
And then there's a magnet. What was it called?
Magnetars.
Okay, what is that?
Magnetars.
Wait. So we talked about the pulsar. What was after the pulsar?
The neutron star.
The neutron star. Does the neutron star build anything or give life to anything or no?
No. Neutron stars are just there. They're again, corpse of the dead star.
So they have no benefit to the.
No.
Zero benefit.
Yeah. Well.
Can they suck things into themselves or damage other planets? Or?
They can definitely damage other planets if the planet gets close to it because they have a very high gravity. So, not as high as black holes, though.
What happens? They cannot suck it in. There's no hole in it.
No, there is no hole, but you will just get
exploded.
Explode, or it will just turn into a steaming puddle.
It will melt.
Yeah, it will melt.
So they have a lot of heat then.
That's right. Yeah, they're very, very hot. Their surface temperature is some 1.5 million Kelvin.
So Let's say a planet so if a planet goes into them, so they suck the planet into themselves, right? What happens? Do they rotate and then they get to the center, or just melt and then there's nothing?
We haven't discovered any planets around the neutron star, but however, we do have discovered one planet around pulsar in 1992. It's called an exoplanet, of course. But the pulsar hasn't the distance between the pulsar and the planet is relatively safe, so the planet hasn't really gone close to the pulsar, which is a good thing. And I highly doubt there are any living beings on that planet because, it's just not possible. Life to exist
in that area,
in that extreme environment, right?
And the other one that is hot, it will basically probably melt everything and that's it.
Yeah.
You become gas, I guess, right?
That's right. Yeah.
That is crazy, man.
So
it's just like burning wood.
Oh, yeah. But 1.5 million degrees hot.
Make kebabs. I'll go make kebabs under my side. Everything becomes a kebab in that field. No, there's dust, nothing. Okay, so what is? Talk about the magnet one.
Magnetars. They are magnetars are the most magnetic objects in the universe.
Even more magnetic than a black hole.
That's right.
Even more magnetic than a black hole.
Yeah.
How does that work? So do they suck in or do they push out?
There is really no object close to magnetars. It's just magnetars by itself, and how we get earthquakes on our planet, on the Earth. They're small earthquakes, right? But magnetars actually get starquakes.
What is a starquake?
Starquakes is getting a earthquake or getting a earthquake on the surface of the star. So basically cracking the surface of the star. That happens in magnetar, and when that happens, you get just insane amount of magnetic field the star is throwing off at anything that's in the way. And in 2002, there was a starquake on a magnetar called SGR 1802-017. So SGR is called soft gamma repeaters. It's a magnetar, type of magnetar, just like X-ray anomalous pulsars. But anyways, so when that starquake happened, and the magnetar was 50,000 light years away from us. Okay, so there is a space telescope called SWIFT, which is designed to look for these high X-ray objects in the universe. Okay. And so that magnetic field was so strong that it actually blocked the vision of that telescope for I think an hour and a half, because the magnetic field was so strong. And it also was shrinking our Earth's magnetic field. And it shrunk our Earth's magnetic field for at least 4 hours, from 50,000 light years away from us.
If we were closer, we would be finished. I guess.
Oh yeah, absolutely. Yeah, it will. Yeah, it will wipe our credit cards. It will basically destroy everything that comes in.
Wipe our debt.
That's right.
No, but okay. So it's a magnetar, right?
Yeah.
Is it like a planet because you say it's a surface?
It's a star.
Okay, so
Yeah,
it's
stars
like
have
a sun,
surface too.
almost like a sun.
Oh yeah.
Is it all magma? What is it like?
We don't know. Okay. We really don't know what magnetars are made of, because we only have a handful of them in the universe, at least in our galaxy, it's the handful of magnetars that we have. They're really far away, and it's most of the time it's quite difficult to actually study what the magnetars are made of.
So, have you seen any of them that there's planets close to them? What would happen? Like seriously, would it?
They won't exist. Planets will never exist around the magnetar. Yeah.
So so how big are they?
Oh, they're only 15 kilometers in diameter, even smaller than a neutron star, and they have a mass of 5 times the mass of our sun.
So if it's 15 kilometers, right?
Yeah.
And I guess how far planets are not safe around it? I guess how many light years? I guess no.
there will be no planet safe around anywhere in around the magnetar.
How
You were
far?
50,000 light years away from us,
And you feel it?
and we felt the effect.
Yeah.
We felt the shock waves of the magnetars, which actually disturbed our magnetic field and also destroyed the vision, the CCD cameras, the sensors of the Swift telescope. So you can imagine from 50,000 light years away, it can do that much. If we were closer to that magnetar, we won't survive.
What would be the safe distance?
There is no safe
Minimum
distance.
safe distance.
Oh, I don't know.
Because I'm just
about
trying to.
100,000 light years away.
Okay. No, because I'm trying to figure out if this thing is in the center of our universe or whatever, right? Galaxy, right? How much space all the other planets are safe from it? Because if this thing is, it can destroy everything, right? So it's just basically, I'm thinking like it's just like there's a light in the sky and there's this giant gap of bubble of this thing because it's destroying everything, right? Would it be like that? Because
No, it won't be like that. It won't really destroy anything because the planets are orbiting, other stars.
Okay.
Right, and magnetar is just really doing its own thing, and these starquakes are really rare.
Starquakes.
Yeah, yeah. We haven't seen a single starquake after that. So they're extremely rare. Yes, actually, yeah.
What are some other stuff that are very interesting? Well, like you have so much knowledge, like it's crazy.
Yeah. What other stuff? There are comets, there are asteroids in our solar system that we look for. We are monitoring the potentially hazardous asteroid, which may or may not have a impact to our planet. We will for sure one day. So we are looking for these specific type of objects in our solar system which may cause a threat.
What are some of them? Let's hear the people.
There is one, but we don't have to really worry about it for at least 1,000 years.
Okay, good, thank God.
Yeah, so we're good on that one. Yeah.
What is it? Is it coming really close or?
It's an asteroid. It's a near-Earth asteroid. Now it's a potentially hazardous asteroid. A couple of days ago, actually, I did some orbital mechanics, the celestial mechanics, calculated the exact orbital path of that asteroid, and in 989.5 years, we'll have a direct impact, and it's about 200 kilometers in diameter, so it's a planet killer.
Yeah, we'll be gone. Hopefully, that's. I don't know.
Yeah, don't want to scare anyone, but I mean there is a possibility of us getting hit by any kind of asteroid.
Any time, right? You never know. Like maybe those magnetars will say something or like pulsar.
That's right. Yeah. So there is a huge possibility that we might get hit by an asteroid. Yeah, we are surrounded by dangers.
So talk about how everything started for you, because you've gone so far, you have all this knowledge. How did everything started for you?
Oh, that's a good question. So yeah, as a kid growing up in India, we didn't really get to see stars because of the light pollution and everything. But during summer months, my parents and I and my brother, we used to sleep on our rooftops.
Flat roofs, right?
Flat roofs, of our houses. And we used to look at the stars, and once in a while we used to see Milky Way. It was rare. It was like maybe 2 or 3 times in in 1 year that we get to see the Milky Way. But yeah, then
how did you feel when you saw the Milky Way?
Really, really good. For the first time. But that was from inside the city, though.
When all the lights and
so much light. All right, so we could actually see only few stars, and now I don't even know if you can see any stars from the city. So I started going out in darker areas nearby the city. My parents bought me a small telescope.
How big was it? Show me.
Well,
it
was about that big. It was a Dobsonian 6-inch telescope, right? It was a smaller one. So
that's probably what most people have.
That's right. Yeah,
Still,
exactly. Yep. Yeah. And yeah, so I used to go in a darker location and do some observations. But yeah, one of my first time going out in a very dark location on my birthday, actually, that was one of the best experience I ever had, because I never had.
Did you go alone or with your parents?
No, I went with my friends actually, and yeah, that was the first time I saw a comet.
Yeah. So you talk about the whole experience. You set up your telescope. Like what happened? Tell me about the whole, because it sounds so exciting.
It was a cold night. I mean, cold meaning it was 7 degrees. It's all warm here.
It's like heavenly here.
Exactly. But at that time, it was kind of a cold winter, beautiful night, and there was a comet called C2014 Q2 Lovejoy. It was the name of the comet. Yes. Lovejoy was the last name of the person who discovered it. We get to name the comets. Yeah. I named a supernova after my wife.
What is it called?
It's called Robin A1 2021, AT 2021 XHC. So yeah, the first name is Robin.
It's registered,
name.
Right?
Yeah. Anyways, yeah. So that night we first observed that comet, and it was a very eerie green color. It was a kind of a fuzzy glow in the sky, and it was also visible to the naked eye. And then we saw Andromeda Galaxy using the telescope, a smaller telescope though. That was and then after that, that's it. Okay, that's what I'm gonna do.
So you fell in love with it.
Yeah.
So tell me, how did it progress to this? Like, how did it happen? Like, then what happened after that?
Yeah, so...
But your parents were supportive, right?
Oh yeah, they were always supportive. Always. They always have been supportive of that, which, I was fortunate enough.
In some cultures, they hit you with a telescope,
Yeah.
You want to come here, doctor.
Yeah. Right. Yeah. No, my parents have always been supportive about, astronomy. They're like, do, what you want to do.
That's beautiful.
Huh? Yeah. I was fortunate.
So what happened after that night?
Yeah, so I went to... at the time, I was also going to university, and I was doing physics, mathematics, and geology. Three good subjects, right?
You're probably really good at this stuff, right?
Yeah.
How good are you in physics?
Good. Like
math?
Good. Yeah.
Oh, good. Geology, you good, right?
Yeah. Well, yeah. I did geology. I don't do a whole lot of geology anymore. Now I mostly do is computer science.
Oh my God.
Yeah, because that's what astronomy is nowadays. So I went to university there, and then I moved here, went to CNC. I did physics courses, and then I got my specialized certificate in nuclear physics. And
nuclear physics?
Yeah.
Wow, you're a genius. That's why I'm like, so I'm listening all the time today. Yeah. So you went, so you were in India, right?
Yeah.
So what you did there that you came here, right? You probably got the scholarships and things like that, right?
Oh no. I some of my parents supported some of my education. Then I worked here, to support my education. Yeah. Expensive, but it's good.
But you love it. Like,
I enjoy doing it, right?
We have such a short life now, especially when we talk. Right?
That's
you might as well do something you like, right? What's the point?
Yeah.
Okay, and then what happened? You came in here and then.
Yeah, and then did courses at the CNC, did some computer science courses, because I realized that, astronomy is not just looking through the telescope, it's mostly computer science nowadays.
Why?
Because everything is robotic, and so to process our astronomy data, which is coming from CCD detectors, we need specific softwares for specific telescopes. They do, astronomers do have their own, observatories do have their own softwares, but a lot of astronomers, one of them is me, who don't like the way they wrote the software. I don't like their processes, the way they did it.
Talk about how.
It's just about processing. I'm really careful, and I take my time in processing the data that to get every single photon out of the data which is useful, right? So I wrote my own softwares on a language called Fortran. It's a 1957 language.
Is it? What do you mean 1957?
So the computer language was written in 1957.
1957.
Yeah, just after the World War II. Yeah.
So this language, what is it? Is it as advanced to ones now or no?
In some ways, it really is. Yeah, it can do a lot of mathematical calculations. I know there is another language called Python. I use Python too, but Fortran is just, for computational work, it's just really good. So I wrote a program for that, and that, now, for example, last night I was observing from two different telescopes. One of my telescope, which is in my backyard, and another telescope is in Victoria. That's not my telescope, that's the government of Canada though. So this morning I got about 955 images from two telescopes combined. Right. So I woke up, downloaded all the data, some 17 gigabytes or something like that.
17 gigabytes.
Yeah, it's not a whole lot.
That's not bad actually. This is gonna be 17 gigabytes.
Yeah, exactly, right. And so after downloading the data, it's pretty much my computer processes everything automatically because I trained my computer to do that, machine learning, right? Yeah, so you gotta work hard to be lazy.
Okay, so you automated it.
Yeah.
What is the difference between your stuff and other people? Is yours more advanced or faster? Or?
I wouldn't say faster or advanced. Yeah, astronomers actually, we use machine learning in almost everything in astronomy nowadays. So some of my friends who are astronomers, they use machine learning for their own. It's just different techniques.
What is machine learning exactly?
Machine learning is making, so it's training the computer with millions and millions of data points. So telling the computer what the computer, you want the computer to actually do for you, right? So, for example, after the data coming from the telescope, then now my computer right now is looking for supernovas. Exploding stars in different galaxies. So my computer will send me trigger on my phone that I found a supernova in this and this location. Right. So I wrote all of that. So that's what machine learning does. Yeah. Your computer is basically acting like a human, but it's a computer.
That is insane. So what kind of computer do you use? You probably use a PC, right?
Oh yeah, I have. I don't know, 18 computers.
You have 18 computers?
Yeah.
18 computers?
Yeah.
Okay.
My wife calls us I have excessive behavior for computers.
Okay, because this thing is going to take a lot of processing power. So do you have all the computers connected to them?
Yeah, I do parallel processing. Yeah.
So I guess you need very powerful processors.
Yeah.
What are you using?
Oh, I have i7, some, I don't know, GX, some graphic card. I have like 3 different towers, which has the good, processing power.
What kind of graphic cards are you using? You're probably using crazy.
I have no idea. I have no idea. One of my friends knows all about that, and he built it.
Oh, okay. How the heck do you connect everything together? Because you have what?
Oh, I have SSH server.
This is getting more complex, man.
Yeah, I know. See, told you, astronomy is complex.
Talk about it, because nobody knows. People, they think you sit and you look through a telescope, and that's it, right?
We don't. No. Telescope look through. The cameras basically look through the telescope, and we look at our computer. We look at our data. That's right. That's how nowadays it is.
That's crazy.
Yeah, it's much easier. I mean.
So when you graduated, then what happened? How did you become a?
Oh well, even when I was in college, when I was in school, I was still doing my research. Right. So I started a team in 2018 called Global Supernova Search Team. It's a international collaboration between astronomers. One of my team members, he is from France, from Argentina, from United States, from India, from Spain. So we have and Canada, of course. So we have a total of 11. Team members, and they're all professional astronomers, and so that was collaboration between astronomers to look for these supernova events in the universe, and so we did well until last year. I have about some 320 publications since 2017 until 2023. So we get time on different telescopes, and you have to show them the work that you're a useful user of that telescope, and you're not just using the telescope and not doing anything. So it's and it's hard getting time on bigger telescopes.
How is it? Like, what do you have to come with a huge portfolio? Or?
You need a very strong proposal and a very strong scientific justification that what you want to do, how you're going to do it, and why you want to do it. Yeah.
What is your favorite telescope till this day?
Plaskett telescope.
What is it?
In Victoria, 1.8 meter. It's a 106-year-old telescope built by John Stanley Plaskett.
106 years old?
Yeah. It's completely robotic now. So that's what I was using last night from Prince George, and it's on the island.
Why do you like it so much? Because is there more advanced things than that or no?
Oh yeah, we do. Yeah, 3.6 meter Canada France Hawaii telescope, the one I also use. It's much more advanced, but there is something about Plaskett telescope that
What is it about it?
I don't know.
It's so old, right? I mean,
it's a very old telescope. That's one of the main things, and I don't know. It's just an incredible piece of history in Canada, and using that telescope at least 17 times in a month for every month.
So you have to write a proposal again and talk to them, or do they give it to you? Did they know you enough to give you access? Or
No, we still have to, write proposals always to get
still
access.
to write proposals? What is that? Like, seriously?
That's government, and we have to follow those processes. But yeah.
Do you have to pay them too?
No.
Thank God. That's the only thing. Application processing fees, right?
No. It's just, no. We don't have to pay. Luckily, we don't. I know, right?
I have some more questions before we finish, right? You remember when you were a kid and you were looking through the telescope? Yeah. Did you ever thought you'd make it this one?
No. Honestly, no.
Why?
No, I don't know. I just that is I never even actually thought, as a kid of becoming a professional astronomer. I never even thought about it. Until my first year in India when I was in university, in my physics class, my very first physics class, we learned about Introduction to Astrophysics, right? And my first geology class, we learned Introduction to Solar System. And when I started learning about that, I'm like, okay, that's what I'm going to do for the rest of my life.
What is your advice to somebody who was your age right now and just got their first telescope and they want to do the same thing you're doing? What is your advice to them?
That's a great question. So we have observatory here in Prince George. It's a beautiful telescope. My advice will be to come out to the observatory, get a chance to, look at the actual night sky, how dark it is, how many stars you can actually see just with your naked eyes, even without a telescope, and then what objects you can see with your telescope, and compare the smaller telescope with the bigger telescope that we have in Prince George. Is a 24-inch, 0.6 meter optical class telescope. So it's a relatively...
Is it computerized?
It is, yes. Yeah, we are in a process of making that telescope completely robotic too. Yeah, and it is really always, you don't always have to do, science. You can be a hobby amateur astronomer as well. Take the telescope out and then just explore the night sky, because there's just so many things to, look in the night sky, just endless. And even with a relatively smaller telescope, you have at least 200 objects to look at.
How can people find you?
You can. I have my email address, which is malhar.kendurkar, Kendurkar @gmail.com. Or you can go to the observatory's website, which is Prince George Astronomical Society. You can type that on Google. And then I have my email there, as well as the president at pgrask.ca. Yeah, or you can find me at the observatory on Friday open house events. So we have open house events every Friday until the second week of April, starting at 8 o'clock.
Yeah.
And there will be always different presentations every week.
Oh man, that's not.
Yeah, yeah.
Do you? I'm gonna ask you maybe two more questions. But before we finalize, do you have anything else you want to talk about?
Yeah, go out, look at the night sky, and also look at the whenever we have clear skies, just look up and try to see northern lights too.
Yeah.
And March apparently is the best month to look at northern lights. So it is. We are in March.
Yeah.
Although there is a full moon coming up, which is too bad. Because it will be in the way. Almost always is, but that's okay. But you can still see, beautiful northern lights and tons of stars. So yeah, it's important to, take a break from everything and go out and look up.
Does your wife share the same passion as you?
She's an astrophotographer and she's a photographer. Yeah.
Oh, wow.
Yeah.
That's why. So you have someone who is, rooting for you.
That's right. Yeah.
That's important, right?
It is. Yeah.
If you didn't have somebody who was like-minded, what would have happened? It would have been right?
Yeah, I don't know. It's a hard question.
So, how do you meet your wife, by the way?
Oh, we actually met at the observatory.
Are you serious? Oh, that's beautiful, huh?
Yeah. She actually came out to one of the course I was teaching at the observatory, and she was the student, and that's how we actually connected. Yeah.
Do you fall in love and then you share the same passions and things like that?
Yeah, we have same similar interest. We're both wildlife photographers, also as a hobby. Yeah.
Oh wow,
Yeah,
there's so many dimensions.
Yeah, and she likes to play some music. I play some music, handpan, guitar and stuff like that. But yeah, we got a lot of same interests. So yeah, we started talking and
Here you are.
Yeah.
What is it important to have somebody who kind of share some things with you in that area?
Yeah, I don't know. One of my close friend, Bob Nelson, who passed away sadly 2 years ago, who built this observatory. He's actually one of my main mentors. Because of him, I am who I am today. And he has supported me a lot with my career in as a professional astronomy, and he guided me a lot.
So it's good to have a mentor.
It's important. It's very important. Yeah.
Are you mentoring people yourself now?
Oh yes, I am. Yeah.
Oh wow! So people can come to you and you mentor them.
Yes.
That's good to know.
Yeah.
I want to ask you something. We can cut it out. Okay, if it's too difficult. Based on the size of the universe, galaxies, and all this stuff, is it possible for there to be other life forms?
Oh, that is a beautiful question, actually. There definitely is life somewhere in the universe. Okay, there is, for sure there is, because if it isn't, then it's terrifying, and if there is life out there in the universe, it's also equally terrifying. Because we are not alone, and even if we are alone, that's terrifying too, because the universe is so incredibly big, and in that big of a universe, if we're alone, that's pretty dark, if you think about it, But yes, there is life somewhere in the universe. We just haven't found it yet because it's really difficult to find life on planets. But in the next decade, I guarantee you, we will find a life.
Oh man, look, hopefully they're nice.
Yeah.
Imagine they see us as chickens.
The life could look like anything. On other planets, we see all these pictures of different aliens with kind of a circular face or oval face. It might not even look like that. It could look like anything. Even the life forms. It could be microscopic or something, but that's still life.
I have a question. When you look at the planets, Are they like round?
Oh, yeah.
Are they oval?
No.
Are they like, there's no flat planets out there, right?
No,
You know, you know what I'm trying to say. I just don't want to talk about it.
They're round.
Everything
Yeah.
is round and beautiful.
Yeah, yeah.
So is there some maybe oval a little bit or no?
Oh yes, sure there are. Yeah, those are called minor planets. One of the minor planets is called Gong Gong.
Yeah.
And was discovered in 2004.
How does it look?
2012 actually,
yeah.
from Mauna Kea.
Yeah.
So that looks like a.
Is it like a football?
Yeah, exactly, like an American football,
Yeah.
right?
How does it work though? Like how does it?
It has a very interesting orbital mechanics. It's orbiting at every different angle, right?
Also, it's not just one angle. It's just turning around. It changes.
It changes its orbit time to time. Yeah,
Imagine if you lived on that.
that would be a bad thing,
Yeah.
or it could be a very cool thing.
So when it's rotating like that, does it have a lot of earthquake on the surface because of the quick?
We don't know really. It's too far away to tell. It's in our solar system, but it's really far away.
What is it called?
It's called Gong Gong.
I'm gonna go research it. I'm very interested. I've never heard that before.
Yeah, Gong Gong. There is Sedna.
Yeah.
And Quora.
Yeah. Do they have like a sun around them or star system around them?
Those are minor planets. Those are part of our solar system. So their main star is our sun.
Oh wow.
Yeah. Those are just really far away in a Kuiper belt. Yeah.
I don't know that. There's so much to talk about that
I
we
know.
could stay here forever. Okay, I'm gonna end it because we're gonna be here forever, and it's such an interesting subject.
Yeah.
So
Yeah. Thank
I
you
want
for
to thank
having
you
me.
so much for going on
Yeah,
this. It was such an
thanks
interesting
for-
experience. Right? Like I love this subject. We could sit in here and then everything. We'd be here 10 years, 10 light years sitting in here.
Yeah. Thanks for having me. It was a great conversation.
Perfect. Thank you very much for. My brain is just gone because there's so much more. I forgot the name of the show because I'm just. Thank you very much for joining us on this episode of Northern BC Narrative on Location, and I hope that you enjoy this episode. But before we go, why is it important to follow your passion?
So it is important to know our place in the universe and where we, how everything started. There are doubts about, if the Big Bang really happened or not, because we have observed the galaxies which are further away than the actual Big Bang happened. So it is, I think, important to actually know what is, what's our place in the universe and, how other stars are exploding and the iron in our body, that has come from the exploding stars, right? So we are literally made of stardust. Carl Sagan actually said that. Yeah.
And that's your passion.
That's yeah.
Beautiful.